Hello students. Let's do some more quick examples with vector spaces and vector subspaces. So here's one that I'd like to show you. So what I'm going to take is I'm going to take my vector space, V is going to be R2. So just pairs where each of the elements are in the real numbers. And I'm going to allow W to be the set of all x1, comma x2, so that x1 times x2 is equal to 0. Okay? So it's the collection of products that are equal to 0. So I'm asking, is this a subspace? Well, and by asking that, I'm also asking, is this a vector space? Is W a vector space? So, but I only have to check two things. Now, first of all, it's not empty. So that means I only have to check two things. I'm going to stick to that. Show it's non-empty, show two things. Okay. Now if I wanted to check to see whether this was closed under scalar multiplication, basically I'll just take an element, let's say W1, W2 is in W. I'll start off by writing it like that, so I save a step, don't need to do that. Thus, W1 times W2 is equal to 0. Okay, now what do I want to show? If lambda is in our field, then lambda times W1, W2 is equal to lambda W1, lambda W2. That's how we define this on lists. Now, what do I have to check? I want to check, is this in W? Well, since W1, W2 is 0, we know lambda W1, lambda W2 is equal to lambda squared W1, W2, which is lambda squared times 0, which is 0. And that's exactly what we wanted to show, because we wanted to show that lambda times W1, W2, this pair, also has the same property that puts it inside W, and we showed it has that property. If we multiply the two things, we get 0. So this is looking promising, like this might be a subspace. But let's check addition. So what would we want to show? Well, if W1, W2, and I have to pick a letter. I can't have you guys pick for me because this is a video. Let's use Z. Let's go all the way to Z. And Z1, Z2 are in W. Is their sum in W? Well, if we assume that this is true, so we're assuming that these two are in W, and that means that W1, W2 equals 0, and also that Z1, Z2 is equal to 0. Okay, so now I want to know what happens when I add these two. Well, W1, W2 plus Z1, Z2 is equal to W1, Z1, W2, plus, I forgot the plus. Okay, so we have this. And I want to know, is the product of these two equal to 0? So is W1 plus Z1 times W2 plus Z2 equal to 0? That's what I want to check. And if I multiply this out, notice I get W1, W2 plus W1, Z2 plus Z1, W2 plus Z1, Z2. And I know that is 0 because W1, W2 is 0. And that is 0. But I have this. I still have W1Z2 plus Z1W2. So I might get frustrated here. I might say, okay, I can't figure out how to proceed. What do I need to do? But remember, I didn't say that this was necessarily a subspace. I asked whether it was a subspace. And this is sort of giving us a hint as to how we might create an example to show that this is not a subspace. So whenever you do the work and you fail, that work is not lost. What this is telling me is it's telling me that if I have two elements that are in W, whether or not the sum is going to have the property I need, which is that the product of the two elements is 0, is dependent on this expression here, W1Z2 plus Z1W2. So let's say I want to create something that might be a counterexample. Well, I'd need a W1W2, which is in W. So I need one of these two to be 0. So let's say I start off with 0, 1 here, right? And over here, Z1, Z2, well, I could try 1, 0, I could try 0, 1, I could try 2, 0, I could try 0, 2, I could try a whole bunch of things. But let's think about that. If I'm trying for my W1, W2, 0, 1, then this is going to be 0. That's going to make this whole term 0. And this W2 is going to be 1. So what's that telling me? It's telling me that if I have a Z1 that's non-zero, I'm going to have a counterexample. So I need Z1 to not be 0. So, and lo and behold, I have this. Now, looking at this now without the variables, this is kind of an obvious counterexample, right? Because this has 0 times 1 is 0. This has 1 times 0 is 0. And this has 1 times 1 is not 0. So what we have is a counterexample. And how would we say that? Well, we'd say 0, 1 and 1, 0 are in W, but 0, 1 plus 1, 0 is not. And that's really all I have to do. I don't have to show any of this work I did up here, because in order to show something is not a subspace, all I have to do is find an example of something that fails one of the two rules. So that means either a vector and a scalar that shows it's not closed under scalar multiplication, or two vectors, like here, that were both in W. By the way, that's an in. That's a little hard to read there. Two vectors that are in W that when I add them together, what I get ends up not being in W. And it's fairly obvious that that's not going to be in W because, well, that's 1, 1, and 1 times 1 is not 0. So that's a nice little example. What you might want to do is you might want to say, okay, what happens if we change this to W1 plus W2 equals 0? So I'm just going to take a new vector space, well, same vector space, a new subset of that vector space, W, and I want W to be equal to the set of all W1, W2, so that I'm just going to do the same exact thing, but with plus instead of times. So I'd like you to check that out. Try to see whether or not that is a subspace. So two things you have to check. Once you know it's non-empty, it is non-empty because, well, obviously if you have 0 and 0, it's going to be non-empty, but it's non-empty for a number of reasons. There's also 1 minus 1, minus 1, 1, all sorts of things there. So that's a little exercise for you to try after looking at this video.